Thank you very much. Yeah, first of all, I should thanks to organizers Natalia, Eduardo, Francesco, George, and also Dirk for this great invitation. Thank you very much. So, Shugang Huang, excuse me, Shugang is here now. Yeah, thanks to Shugang. Yes, I forgot, sorry. Great. Yeah, this talk is based on two works. The first is an earlier work in collaboration with Matthias and my former student, Omid, and an upcoming work, again, in collaboration with Matthias, Dirk Rischke, and Xinyan Wang. And as you see, yeah, I'm going to talk about this comparison between these two kinds of theories. In this conference, we heard several talks about causal and acausal theories of diffusion, BDNK, MIS, and these things. Here, I'm going to look into these two theories from a little bit different angle through the lens of correlation functions, and in particular, Schwinger-Keldysh effective field theory. So to address the topic, let's take a look at this outline. I will be firstly discussing, briefly review this conventional theory of diffusion proposed by Fick, Fick's law of diffusion, which is kind of a causal theory. Then we will discuss how to find a UV completion for this theory. Maxwell-Catenio theory could be a UV completion for this conventional theory. Dissipative aspects of this theory, Maxwell-Catenio, and also conventional theory will be discussed in details. In the linear response regime, we will see that there are two different behaviors, underdamped and overdamped behavior. And both of them can be realized experimentally. That's important. However, which is finally important for us in this talk, is to link between these dissipative aspects and fluctuations. So this can be done through two different frameworks, traditionally a stochastic framework, and also hydrokinetic approach proposed by Stony Brook groups a couple of years ago. However, we will see that Schwinger-Keldysh effective field theory, which was discussed also by other speakers in this conference, could systematically incorporate the effect of fluctuations and dissipations into a field theory formalism. We will focus on this topic, Schwinger-Keldysh effective field theory. Then we will present a concrete example of Schwinger-Keldysh effective field theory, which is exactly a theory associated with conventional diffusion. Then we will see that there are some precision tests predicted by Schwinger-Keldysh effective field theory for this conventional theory of diffusion. But the main part of this talk will focus on proposing some precision tests for causal theory of diffusion, or let's say Catenio theory. And this will be done by introducing some scaling functions. So as a first part, let's look at this familiar picture. We want to consider a system at fixed temperature, a fluid system at fixed temperature in global equilibrium. The fluid velocity is also fixed. Then we can create some disturbance of some conserved charge. It could be any kind of conserved charge. Then due to microscopic interactions, this disturbance starts spreading into the medium like this. And finally, it reaches equilibrium. In equilibrium state, again, the density will be uniform through the entire space or entire system. At some intermediate time like this, we will have some non-vanishing outward current of this density like this. The point is, if this time is much larger than any microscopic time scale, this current can be macroscopically given in terms of just, as you see, gradient of density. This was proposed by Fick. And then when combined with the conservation of density, we arrive at this simple Fick's law of diffusion. So this is a first order differential equation in time. So this has some acausal behavior. It can be simply understood if we try to solve this equation by considering the same boundary condition. You see that this textbook result has some acausal behavior in the sense that right after t equals 0, this n is non-zero in the entire space. So in some sense, it violates causality. But the point is, according to this idea here, that we should use this equation after a sufficiently long time, which is actually the idea of hydrodynamic effective field theory. We should keep this point in mind, that this equation should essentially use in the long wavelength limit or in the small momentum limit. So this means that this equation has been designed to work at a small momentum. There is a K star upper limit for K. And okay, I forgot to say, during this talk, I will be referring to this theory as theory A, this conventional theory of diffusion. I forgot, sorry. So for this theory A, there should be some K star that theory works well below K star. However, mathematically, one may want to extend the range of applicability of theory A to larger values of K. But this may lead to some inconsistencies. For example, if we calculate this velocity, we see that if we take K sufficiently large, this may exceed the speed of light. Then this violates causality. So, but one thing is there which prevents this violation, and that is the emergence of a new physics beyond some another scale. This Kc is the scale at which a new physics emerges. How to model this new physics? We need to introduce a theory B, another theory. This theory B that could resolve this problem, this inconsistency, should have at least two characteristic modes. To capture the physics beyond Kc, we need to have these two modes, omega 1 and omega 2. What is omega 1? Omega 1 is a diffusive mode which remains valid even beyond K star across, as you see, this interval. Omega 2 is a fast relaxing mode which specifies the physics beyond Kc. And the interaction between omega 1 and omega 2 specifies the scale Kc. Good. So we can extend this picture. We can try to introduce other theories, like theory C, for example, which captures the physics even beyond another cutoff, Kc prime. But we focus only on theory A and theory B in this talk. So to understand more about these two theories, let's take a look at them okay, let's first see why theory B can fix the problem. The emergence of this new physics is very similar to introducing a relaxation time. This was done by Cattaneo in this seminal paper. The idea is that the acausal behavior of fixed law of diffusion, or theory A, is directly related to instantaneous response of system to external sources. So in order to remedy this problem, we need to introduce a relaxation time. The idea is to take, again, this current proposed by Fick, add a relaxation time on the left side, combine with this equation, and then we arrive at this second order differential equation in time. We all are familiar with this kind of things. And then when we solve this equation, we see some kind of a slower spread of disturbance into the medium, and the problem of acausality could be resolved. In Fourier space, this equation has two modes, as you see here. We can consider two different limits, two different regimes. When tau dk squared is taken to be sufficiently small, we see that these two modes simplify to, okay, again, familiar diffusion equation or diffusive mode together with a gapped mode. In this frequency plane, I have illustrated these two modes. Then if you limit yourself to the physics inside this semicircle, physics can be entirely described by theory A. We don't need to work with theory B. In other words, theory A is nothing but the theory B in this limit. So this is a comparison between these two theories in this complex frequency plane. However, when tau dk squared is taken to be large, theory A doesn't work properly. And then you see that this d omega over dk approaches a finite value. You need to take tau to be non-zero to prevent acausality. This is important. Good. These are all familiar things. Now the question is, to which kind of systems, physical systems, these two theories could apply? This is a very important question. As we may expect, theory A is kind of universal picture, like hydrodynamics, could be applied to late-time dynamics of all diffusive systems. However, theory B is a little bit different. Theory B can be viewed as MIS theory, Mueller-Israeli-Stewart. In MIS theory, the idea, one idea at least, one of the approaches is to take tau as a UV regulator in the sense that it's just used to resolve the problem with the UV sector of theory. However, it does not have any effect on the low energy physics in the late time dynamics. I think we discussed about this during the Rajiv's talk yesterday, more or less. But we do not take this approach here. This is not our approach. The idea in this talk is that we look at theory B to apply to a very special class of systems. This special class of system has this special spectrum of hydrodynamic and non-hydrodynamic modes. As you see, there is a well separation between these two modes, the two modes of theory B, with the rest of non-hydrodynamic modes in these systems. If you have such a system, we can apply theory B properly. How? As you see, omega 1 is a diffusive mode. Again, omega 2 is that non-hydrodynamic mode, and we have also other non-hydro modes. They should satisfy these conditions. And the point is, this is not a theoretical construct. You can find such systems in nature. For example, QCD near the critical point has more or less the same situation. Magnetohydrodynamics, we have many examples in condensed matter physics. So this could apply to a large class of systems. Although, compared to theory A, it's special. Good. Let's take a closer look into these two theories again. I would also emphasize that the idea is to finally compare these two theories by considering correlation functions. So far, I'm just kind of reviewing known things. Good. In theory A, as you see, okay, again, theory B, with these two modes well separated from the rest of non-hydrodynamic modes, let's assume that these two modes of theory B themselves are well separated from each other, so that omega 1 lies close to the origin, and omega 2 close to this blue semicircle. In this case, omega 1 should be of order dk squared, omega t more or less of order 1 over tau, since dk squared is much smaller than 1 over tau. In this case, inversely, in time domain, we can say that tau is much smaller than 1 over dk squared. This is definitely a special case for theory B. If we restrict ourselves to frequencies of order omega 1 or even smaller frequencies around this region, then in time domain, we will have time scales larger than 1 over dk squared and much larger than tau. And this is exactly the regime of applicability of theory A. So this is another way of saying that how theory A could compare with theory B. Good. Yeah, please. Right. Right, right. Right, right. I think finally correlation functions reflect this kind of a spectrum that we see here. They should be equivalent to each other. So if we have such kind of a spectrum here from correlation functions, we will get the same result. They are absolutely the same.
I mean, the question is, can you isolate unless you have a system with finite size?
Right. This is another question. I would assume that we are working with such a system. Thank you. Good. So this separation of scales simply suggests that late time dynamics of the system is given by this simple damping behavior. Again, familiar from textbooks, e to the power of minus dk squared t coming from this part. With some corrections in terms of powers of tau dk squared. This is the physical, late time physical behavior of theory A. However, in theory B, we can allow for a broader range of values for tau dk squared. In other words, tau could be even of the order of 1 over dk squared. We don't need to consider this sharp separation of scales. Then, if you consider this, the late time dynamics should be given like this, a multiplication of two functions. What is this? When you have this kind of relation between the time scales, the dominant frequency scale in the system is neither tau nor 1 over dk squared. This is the dominant frequency scale, the frequency at which these two modes collide, 1 over 2 tau, roughly speaking. So then we will have this damping, exponentially damping factor together with a non-perturbative function of tau dk squared. If tau dk squared is small, this function should behave in such a way that the entire function gets back to this expression. However, tau dk squared could be large, could be of order 1, whatever you want. So this is a rough prediction of the late time dynamics for theory A and theory B. You can approve these predictions explicitly by solving the linear equations for these two theories like this. The trivial, again, another textbook result. This is kind of, again, should be a textbook result, but not so well known as the first result. As you see, we have exactly the damping factor that we discussed on previous slide together with this more or less complicated function of tau dk squared. So depending on the sign of 1 minus 4 tau dk squared, there are two different regimes, as you see here. If this is positive, this quantity, this function behaves exponentially damping like this. We call it overdamped regime. And when this is negative, we will get this kind of oscillatory damping behavior. Interestingly, both these two behaviors can be realized experimentally. In this recent paper, please. Very good. In this case, we need to apply only one initial condition. But in this case, we need to apply two initial conditions. The second initial condition is to take the n dot equals 0 for any k. Then you will get this. But regardless of what kind of initial condition you take, the late time dynamics is given by this function, finally. That initial condition affects this initial point here. So this finally, this kind of decoupled from the late time dynamics. You will finally get this kind of damping oscillatory behavior. Yeah, but that's a very important point. Thanks. Yeah, please. This comes from the point, okay, good point. Everything I think is related to the sign of this quantity, this expression. So for this, I think it's meaningful to take this part outside and then. Because, very good, this part is always exponentially decaying like this. So we have two modes. So, but these are our two modes. I think the idea behind this picture is that the exponential behavior is encoded in this point. So e to the power of minus t over 2 tau comes from this point. These two guys could be here or here. If they could lie here, you will get a diffusive mode together with a damping mode. Then you will fall into this class. But if these two modes are locating like this, you will fall into this class. So for me, I think it's, I don't know, maybe we should refine this presentation, but the point is, this collision point is kind of important as a dominant frequency for this picture. Good. So what is this experiment? In this experiment, this kind of condensed matter experiment, a two-dimensional lattice of lithium atoms are subjected to some external optical potential. Interestingly, this is a two-dimensional lattice, as I said. And then the idea is to let the spin of lithium atoms interact with the external magnetic field. At some point, this external magnetic field suddenly switched off, and the spin starts spreading into the medium, relaxing out. So there are two kinds of data coming from this paper, this experiment. You can take it, you can consider a row of atoms within this lattice, and then consider different snapshots of spin profile. As you see, starting from this time, you see that the spin is gradually relaxing out. This is related to one special row in this system. Or you can also take a look at one specific site within the system and see how the spin average changes over time. Different, okay, you see 4 different data sets with different colors, blue, red, and so on. And then since, according to this paper, according to what the authors say, since the amplitude of external potential is small, the system operates in the linear response regime. Then the idea is to feed these data to the solution of linear equation of theory B. We saw that solution on previous slide. So by making this fitting, you can find relaxation time and D. So while in MIS theory, tau is not a physical observable, is not a physical quantity here, tau a physical quantity and can be measured experimentally. This is the first message. The second message is that you see exactly the two behaviors that we introduced on previous slide, overdamped limit and underdamped limit regimes. So it's nice. Theory B can be realized experimentally. Good. Excellent, sorry, forgot to say. Different colors are related to different values of external momentum of the potential. We have an external potential. This external potential is kind of, you have a sinusoidal function, so you can consider some wavelengths or momentum for this external potential. Depending on that k, you will have this different values of k, different values of tau dk squared. So this determines if your system behaves in the overdamped limit or underdamped limit. Is it clear? No, tau is constant in this system, I would say. Tau is constant. Depending on the value of k, this will change. So if this value is small, for example, then you will get this red part of data. For larger values of tau dk, though, depending on your k, you change your k, and then you will get another set of data. Yes, but the idea, okay, very good. The idea is that this kind of initial condition will finally propagate into the system. You will get, yeah. Good. And then, yeah, so far, as you see, we discussed dissipative aspects of theory A and theory B. All things are dissipative, but we can go a little bit more deeper and think about microscopic aspects of these theories by looking at the fluctuations. You know, the origin of this kind of diffusion or diffusive theories are finally Brownian motion of particles. Then we can consider the idea of Landau-Lifshitz. The idea of Landau-Lifshitz is the conservation equation or the hydrodynamic equation that we started with is nothing but some kind of noise averaged equation of some more fundamental equations. This more fundamental equation, as you see, with these noisy variables is called a stochastic diffusion equation or a stochastic hydrodynamic equations. J, this noisy J, can be defined like this. Rajiv told us about this yesterday. This N is some noisy density. Psi is the noise field. And I have also let this D non-linearly depend on density for some later requirements. Good. Now the point is, the idea of Landau-Lifshitz is that at late time line distances, all physical observables are averaged over noise. This is the most important point. So let's consider density, this noisy density, as a sum of two parts. An average value, this could be a solution to non-noisy hydrodynamic equations together with the noisy part. And let's also assume that the noise distribution is Gaussian. Then the goal is to calculate the average of this current at late time. If we restrict ourselves to linear response, D must be kept as a constant, must be taken as a constant. So in linear response, this guy vanishes because this, as I said, we are assuming that the noise distribution is Gaussian, and the effect of averaging over this part gives you the classical current of diffusion. So in linear response, there is no any noise effect. Beyond the linear response, when we take into account the effect of nonlinearities, things are different. From this term, we could get a 2-point function of delta n, which is kind of a new contribution to the average of current. This guy is called, this quantity is called hydrodynamic fluctuations. And you know, this is kind of equal time correlation function. Landau-Lifshitz doesn't discuss this part too much, but we want to calculate this quantity concretely and then see what the effect of this term on this average is. This can be done through other frameworks. One very clear framework is the hydrokinetic framework proposed by Stony Brook groups a couple of years ago, as I said in the introduction. The idea is to start this noisy diffusion equation. As you see, we have a noise on the right side, and then construct a kinetic equation for the equal time. I would emphasize on equal time. We will discuss this later more. And then construct a kinetic equation for this equal time correlation function. As you see, this is not a conservation equation, not. This GNN relaxes towards an equilibrium value which is fixed by fluctuation dissipation theorem. So if we solve this equation, we can find some information about the equal time correlation functions I showed you on previous slide. Now let's see what the effect, what the contribution of this two-point correlation function average of current could be. So again, a stochastic current I have expanded in terms of density around equilibrium state. It turns out that we should calculate this integral over solution of this equation. This integral is kind of integral in momentum space. You need to consider a cutoff. And here is the result. The first term is familiar to all of us, classical diffusion. But we will get two new contributions. One coming from the cutoff, a UV-dependent, lambda is cutoff, a UV-dependent part, and a UV-independent part. This UV-dependent part, like in conventional quantum field theory, can be used to renormalize transport coefficients, thermodynamic quantities you are familiar with. But this non-analytic part in frequency space gives a power law decay in time domain. And this is nothing but the long time tail of hydrodynamics, in this case for diffusion. So please. Correlation function. Right. Right. Uh, uh, good. So your point is that, okay, I think it will be more clear when comparing this object with the non-equal time correlation function. But now I would say that if we look at this GNN at times much larger than the microscopic time scale, then this would make sense. GNN could behave. Okay, we can perform Fourier analysis, and I don't see. GNN T should not depend on T. Why? Right? In equilibrium, right? Yeah, the point is this quantity has not equilibrated yet, has not thermalized yet. We are trying to see how this quantity reaches equilibrium. This is the question that we want to answer. Over noise, exactly, over noise. So the point is, in conventional hydrodynamics, we always assume that this quantity is in equilibrium. So the only evolving objects are densities. We do not think about two-point correlation functions. But for QCD near the critical points, these objects are essential. Mm-hmm. Mm-hmm. I think I would like to emphasize that, no, in a patch of fluid, we have two points separated from each other by delta x, let's say. Then the question is, are these 2 points in local equilibrium or not? Right, right. Sum over phi. You mean in the path integral? Oh, okay, good. Right, right. Exactly. Integrating over n. Well, sorry, by integration you mean in path integral. Okay. Okay, if you give me the noise distribution function, I would do that. I believe. Okay, got it. So you mean, I see. I see, I see. I need to elaborate on this in more detail, but I wouldn't see, okay, I didn't think like this. I think we should discuss more about this. Although I think this works consistently. There should be some clues that I have probably overlooked. Good. And then, yeah, as you see, this is the long time tail. Well, okay, these questions are related to the fact that conventionally, traditionally, we derive long time tail from non-equal time correlation functions. But it's a little bit weird that I am trying to derive these long time tails from equal time correlation function. But it's kind of things that was done firstly by Rectine and collaborators, and then by Thomas and other groups. But I think I should clarify these details. Good. And then, okay, the point is, as you see, we have two kind of correlation functions, as I said, non-equal time and equal time correlation functions. These problems that Akash also pointed out could arise here, but Schwinger-Keldysh effective field theory more systematically studies these kind of correlation functions. And in the rest of this talk, I'm going to focus on this part. And interestingly, as was discussed, I won't derive equal time correlation functions anymore. I will be focusing on non-equal time correlation functions derived from Schwinger-Keldysh effective field theory. Good. So briefly, in only one slide, I can say that the idea behind Schwinger-Keldysh effective field theory is the idea of studying real-time dynamics in quantum field theories. You know, when trying for that, you need to put your quantum field theory, your microscopic quantum field theory on a CTP contour. In this case, when your quantum field theory at finite temperature, you need to consider a Gibbs density matrix at -infinity, for example. And then the idea of effective field theory is to integrate out fast degrees of freedom, so you can formally separate between slow and fast degrees of freedom, integrate out chi modes, and then you are left with var phi modes. On the other hand, since we are interested in hydrodynamic limits, in the late time dynamics, the only relevant variables are densities. So finally, we will be working with J mu density. So then this J mu should be a function of this phi, this var phi, a slow degrees of freedom of this coarse graining picture. What is this R? R denotes the physical field. We have also var phi A, which is the noise part of this field. Now, the main point that we want to do today is to calculate correlation functions. To do that, we need to couple our densities to some external sources and then functionally differentiate the generating functional with respect to this external sources. So you may have expected, you may have guessed that the next step is to construct generating functional. The generating functional, carries all information about our theory, but we cannot calculate this. We do not want to calculate this generating functional at the microscopic level. In this effective field theory picture, the idea is that generating functional can be written as a path integral of this slow modes, phi r and phi a fields. And this effective Lagrangian carries the whole information about our effective picture. Schwinger-Keldysh effective field theory is to construct Lagrangian just based on some general arguments like symmetries. For example, in the simple case of diffusion, unitarity implies that every term in your Lagrangian should have at least one factor of phi a noise field. So then you need to consider this noise expansion. Let's restrict ourselves to the first two terms, linear in noise and quadratic in noise. Then if you vary this Lagrangian with respect to phi a to find the Euler-Lagrange equation associated with phi a, you will get this E. But what is your motion in this effective picture? Diffusion equation, hydrodynamic equation. So then this means this E phi r is nothing but the diffusion equation you started with. Good. So what about the second term? Every kind of perturbation in your system should finally reach equilibrium. Then you need to apply KMS condition to ensure this kind of evolution. KMS fixes this part. So as you see, starting with hydro equation, you can find the quadratic part of your action like this. A combination of unitarity and KMS predicts that there exists a current whose divergence is non-negative. So second law of thermodynamics is kind of emergent in this picture from the first two conditions. You see that Schwinger-Keldysh effective field theory can be constructed like this. Then you need to apply other things, derivative expansion, going higher in phi a fields and so on. Let's just restrict ourselves to this picture. Now, a concrete example. A concrete example was firstly, based on many well-known works, was introduced in this interesting paper by Chen-Lin, De La Cretas, and Hartnoll. As you see, here is the Lagrangian associated with the diffusion. The first two parts, as you see, are quadratic in phi A and then phi A and N. So these are in correspondence with free theory in conventional quantum field theory. From this free part, we can derive CPT correlators. These correlators, N phi A and N correlators, can be used to find physical correlators. What is a physical correlator? Physical correlators are the result of functionally differentiating the sourced Lagrangian source generating functional with respect to external sources. And this is the density-density correlation functions that are familiar to us, again, from textbooks. And what is this part? This part, as you see, contains cubic and quartic terms, very similar to interacting in field theory, interactions in Lagrangians, for example, in scalar field theory, gauge theory, that are familiar to us from QFT courses. Then by performing loop calculations, for example, you can also find corrections to these physical correlators, very similar to what you do in conventional quantum field theory. Let's, yeah. Exactly, in this case, exactly. Exactly, you're right. Yes. So Pavel pointed out a useful point, I think. Well, what are these lambda prime coefficients, lambda t, lambda? These are just the result of expanding linear response coefficients in terms of n. For example, this d diffusion constant is a function of n. If you expand d as a function, you will get this kind of things. D as a function of n can be written d naught plus like this. This d prime is related to, for example, lambda prime, and so on. Oh, thank you. And then, yeah, here, the thing that I'm going to do is to see what these two Fourier space correlation functions tell us about the diffusion and no diffusion. Let's take a look at this linear response result. The lower half of frequency plane, the other one in the upper part, as you see. Oh, yeah, please. So, symmetric correlation function, great, yes. Right. Yes, exactly, because path integral is an integration over both of them. I totally agree with this, but for the previous points, I should think more. Thank you. So then, yeah, as you see, we have two poles. What is this pole? This pole corresponds to the pole of retarded Green's function. This one corresponds to the pole of advanced Green's function, because as Akash said, this is kind of symmetrized Green's function containing the whole information about both retarded and advanced Green's functions. Okay, so far so good, or familiar to us. But let's go to the next part, nonlinear response, or one loop correction to correlation function. The structure is a little bit more complicated, as you see. We have two second-order poles because of this power here, and also a square root singularity. Here is a structure. These blue poles are exactly the linear response poles, but now are promoted to become second-order pole, as you see, because of this. And we have two branch point singularities together with two branch cuts. The branch point singularity, okay, the location is given by this expression. Here are some questions. Why this location? And what is the origin of this kind of branch cut discontinuity, branch point singularity, and so on? Let's discuss these things in analogy with what we know from quantum field theory. Okay, here, you know this picture from Peskin-Schroeder textbook. I have taken from that textbook. What is this? You study a scalar field theory in Peskin, Schroeder, and then, as you see, we have this linear, let's say, similar to linear response. This is kind of three-level correlator. By considering loop effects, you will get this kind of corrected Green's function. The analytic structure of these Green's function or equivalently, the analytic structure of a spectral function is given in this beautiful picture. Here is a pole corresponding to the pole of this Green's function, and we have a branch cut discontinuity starting from this branch point singularity, which is the so-called two-particle threshold. Paskin-Schroeder, PS find this two-particle threshold by explicitly evaluating a Feynman integral. Calculations, are not easy. You can follow in Paskin, but are easy but lengthy. Honestly, they are lengthy. Then show that they also argue that this two-particle threshold is related to the situation where the two lines of Feynman loop, Feynman diagram go on shell. If you make the two lines of this Feynman diagram go on shell, then you will get this discontinuity starting from the branch point. Instead of explicitly calculating Feynman loops, Feynman integrals, there is a more clever way proposed by Landau in 1979 in this very beautiful paper. I don't explicitly cite that paper, but you can find it easily. The idea of Landau is to find this branch point singularity or this threshold singularity just by finding the pinch singularity of Feynman integral. Let's apply Landau's method to a simple loop diagram in theory A, Chen-Lin, De La Creta's, Hartnoll's work. Here is a loop, you see, we have two lines. The idea is to force the two lines go on shell. So we have these two on-shell conditions for this and this. Then Landau argues that combining these two conditions, you will get this kind of expression. You have three variables here. K prime is the integral variable. K and omega are the external frequency and momentum. For simplicity, let's set K to be a constant value. So K is constant. Now we can vary K prime. By varying K prime, we will get different values for omega. These values of omega form a line of discontinuity because they are coming from on-shell conditions. Your lines go on shell and your integrand becomes singular. So by varying K prime, you will get a line of discontinuities. This gives you a branch cut. But the point is, at one special point, these two conditions pinch the integration contour. Integration contour for K prime is from -infinity to +infinity, like this. We have two on-shell conditions. At any of the K prime, you may have the chance to deform your integration contour to avoid the singularity. However, at a point where your integration contour is pinched from the two sides by these two conditions, you have not this chance. That is a genuine singularity of your integral. This is the idea of Landau. And then it turns out that for this simple example, the pinch singularity, this point is pinch singularity. It's called pinch singularity. The pinch singularity of this integral is at k half. If you substitute this simple k half into this expression, you will get the branch point singularity I showed you on previous slide. So we see that the origin of this branch point singularity is nothing but a pinch singularity of a loop integral. Good. These are mathematical things, but are beautiful. Then we can, okay, in this paper, you can see the introduction of this topic, Landau's paper, in the context of hydrodynamics in this paper. Good. And then it's a good point to, it's a good place to see what the effect of these poles, let me go back to this slide. Okay, how these poles, branch cut and branch points, show off in time domain. Okay, please. Any similar, sorry? Right. Excellent. Landau argues that this kind of procedure can be extended to higher order perturbation theory. And one of my future directions in the research is to apply this to second loop calculations. The question, but sorry. Exactly. Sasha Grozanov and collaborators has applied more or less the same ideas for a special class of diagrams in theory A, not for the whole diagrams, but they have successfully found a very nice structure for the higher order loops in terms of these singularities, exactly. That's one part, but you need to find the pin singularity because this is important, Unshell condition gives you this, branch cut. Pinch singularity gives you the branch point. Extremum point of a function, better to say. Good. Yeah, thanks for the comment and thank you, Pavel. Yeah, Sasho has a paper about this, Sasho Grozdanov. Please. Good point. We have been careful about this. You should, if the two poles lie in the same semi-plane, you don't get any important things. But if the two of them are locating one in the lower half, the other in the upper part, you will get a non-vanishing result. We have been careful about this. And this, yeah, here is the result. Good. So the question that I'm going to ask now is how these poles, branch cuts, and these things show off in time domain, in the late time dynamics. Okay, let's see. Again, in linear response, you have this pole. Let's just focus on lower half plane. By closing the contour like this, we will get this result. We saw this expression earlier as a solution for theory A equation. But now we see that the symmetrized correlation function has the same structure. Now, let's move on to the nonlinear response or one loop correction. We have this structure, branch point and branch cut. Let's focus on very late time dynamics. Then we can expand this this more or less complicated function around this branch point. And by performing analytic calculations, you can close the contour like this in such a way that it encompasses the branch cut properly. You will get this final result. The correction to symmetrize Green's function has two parts, as you see. A damping factor, which is not the same as this. You have a factor 1/2 here, together with the non-local function of time. This is nothing but a multiplication of two linear response damping factor, because there are two particles, there are two excitations in the loop going on shell. You have two of them. Now, when you replace K prime with K1/2, this gives you exactly this. So this coming from this branch point singularity. Please. These are not equal time. Non-equal. As I said, in Schwinger-Keldysh, I just focus on non-equal time correlation function. If you want to study equal time correlation functions in the context of Schwinger-Keldysh effective field theory, I know only one paper by Iin and Sogabe. You need to derive Schwinger-Dyson equation associated with Schwinger-Keldysh. This is something that is known in the literature. But here, the focus is on non-equal time. Yes. As I said, I need to think more about this. Thank you. Good. And then this non-local part definitely is the result of branch cut, the distribution of poles along this discontinuity, which is a line time tail. So we see that line time tail can be derived also from this systematic picture of Schwinger-Keldysh. Good. I think I have only 3 minutes, but I have a lot to say. Okay, great, thank you. So recently, these things have been tested against some very interesting simulations by Della Cretas, Abanin, and Michailidis in this paper. They have taken a step further than this. As you see, they have calculated NN, this non-equal time correlation function, in time domain and in position. The result is given by this. The first part, again, is Landau-Lifshitz textbook result. F naught naught is e to the power of minus y squared over phi. Why is this? You know this from all statistical physics textbooks. But the second part is one loop correction. One loop correction is given, by this combination, a non-universal factor together with a universal dimensionless function. This non-universal factor contains susceptibility, diffusive constant, and d prime. D prime is exactly this guy. Derivative of diffusion with respect to density. It's kind of coupling constant for this Schwinger-Keldysh effective field theory. Good. And then by doing some simulation on a lattice gas with known dependence of d on n, they get this very interesting result. The dashed curve, what is this? This is the difference between simulation result and linear response result. According to Schwinger-Keldysh, the difference should be given by this universal dimensionless function, mathematical function, this dashed black curve. Interestingly, the result of simulation matches perfectly with this. So for this, they refer to this result as a precision test for Schwinger-Keldysh effective field theory. D of n, diffusivity in terms of n. Yeah. You can see more about this experiment in that paper, but I'm not so expert on that area. The result is amazing, as you see. A complete agreement between Schwinger-Keldysh effective field theory prediction at one loop, and also this simulation. So this is kind of precision test for Schwinger-Keldysh effective field theory. You should ask them, I don't know. So honestly, I don't know. So, and then, what we have done with Matthias and my student Omid, parallel to some other works done by Akash, Pavel, and also Chicago group, we have constructed a Schwinger-Keldysh effective field theory, not Schwinger-Keldysh. Our idea was to construct an MSR effective field theory for theory B. So far, all discussions was about theory A. We constructed this Lagrangian or effective Lagrangian theory B, but later on, Akash and Pavel discussed that this could be also a Schwinger-Keldysh effective field theory under some circumstances that I will discuss. And then in this framework, we calculated symmetrized Green's function, symmetrized correlator. You see, again, in agreement with our previous results, we have two poles like this. And the point is, in this case, without performing any loop calculation, we can predict there must be 4 branch point singularities in the structure of correlation functions at one loop. Why? Because, according to Landau's argument, we have 2 lines in this loop. Each line can carry one of these 2 modes. We have 4 chances. Mode 1, mode 1, mode 1, mode 2, mode 2, mode 1, mode 2, mode 2. So we see that there are 4 different behaviors to find pinch singularities. And by explicitly performing loop calculations, we confirm this prediction. This is kind of approved. This is the one loop corrected correlation function. And I'll be showing you the structure of branch points and branch cuts in detail for different values of tau dk squared. If tau dk squared is small, you will have these 4 branch points, 2 branch cuts, and 2 poles. These are second order poles coming from linear response. When tau dk squared increases, these 2 branch cuts move towards each other, finally collide at some specific value of tau dk squared. By further increasing tau dk squared, these 2 branch cuts, they form 2 separated branch cuts like this. So unfortunately, we haven't been able to perform inverse Fourier analysis to find real-time correlation functions for this complicated function. However, in two special limits, when tau dk squared is taken to be sufficiently small and sufficiently large, we have been able to perform inverse Fourier analysis. And now I'm going to show you those results. In this limit, which I refer to as overdamped limits, when tau dk squared is much smaller than 1 and tau omega is more or less the same order, you see we have this picture. This pole, this branch point lies very close to the origin. You can, since omega is small, you can limit yourself, you can restrict yourself to the physics inside this semicircle. Forget about other things. Then you will get this familiar picture. By analytically performing inverse Fourier analysis, you will get the PRX paper result. This simply repeats the previous statement that in the overdamped limit, theory B reduces to theory A. This kind of known, not a new result. The new result is there. In the underdamped limit, when tau dk squared is much larger than 1, we had this picture. By further and further increasing tau dk squared, these two branch points finally coincide. We will get this picture. We will end up with 2 second-order poles coming from linear response, 2 second-order poles coming from the contraction of branch cuts. We can perform this inverse Fourier integral analytically, this kind of textbook calculation. We will get this result, a linear response function together with a one-loop correction. As you see, for both results, overdamped and underdamped limits, we have a non-universal factor together with a universal dimensionless function. A non-universal factor, a universal dimensionless function. Let me show you these two functions, FC and GC here. FC was found by this PRX paper, and here is our result. The universal function in the underdamped limit. You may ask, are these universal functions important at all? The answer is more or less yes, I would say. And why? At least for two reasons. As the authors of PRX paper say, these can be used to do some precision tests for Schwinger-Keldysh effective field theory. They do so for overdamped limit. We can do the same for the underdamped limits, for QCD near the critical point, magnetohydrodynamics, and cold atoms. But more importantly, I think it's the last message of this talk. More importantly, we can use these scaling functions to make some nonlinear predictions for our system. How? And yeah, please. In the limit, in this limit, tau dk squared, tau omega, this is the range of universality of theory. I think it depends on your system. We should see, exactly, you're right. So, good. And then, as you see here, this was the experiment that I showed you earlier. From this experiment, the authors can derive the value of diffusion constant, tau, other physical quantities just from linear response. Now, what is the idea of our work? We think that in the underdamped limit, we can increase the amplitude of external potential. Then system goes to the nonlinear response limit. In the nonlinear response, we have this universal and non-universal things. Then we should fit the data of that experiment with this function to extract what? Tau and D have been already found from linear response. We can find lambda D coupling constant from this new fitting. This lambda D is encoded in this vertex. Then we can use this vertex to make some predictions for example, 3-point function, nonlinear response. You see, a combination of experiment, linear response experiment, together with our universal functions allows us to make some predictions for nonlinear response. Again, linear response with Universal functions gives nonlinear response. This is the predictive power of Schwinger-Keldysh effective field theory. Sorry, I run out of the time. So I skipped these parts, not important. So fast. I just say that these things could be all extended to the case of hydrodynamics, MIS hydrodynamics, finding, let's say, universal functions for B theories of hydrodynamics like this. And then what is important for us as the next part, it was pointed out by Akash and Pavel in their paper, our calculations for theory B are valid in this limit, are valid if we take tau and sigma, both of them constant. Fortunately, all of our results are insensitive to the value of sigma prime and tau prime, luckily. And then the next step could be consider a theory where tau and sigma are not constant. And repeat these calculations and find systems to which we can apply these results. And sorry for running out of the time, and thank you very much for your attention. Thanks. Right. 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 To confirm if I've understood your point correctly, you are comparing this work with holography, or you are talking about two different regimes in this theory? Right. Right. Oh, one mode on imaginary axis, and then in addition, two modes like this. But this theory has only two modes at linear response. So this theory B, has only two characteristic modes. Yeah, I think we could construct other theories, but this theory is important in the sense that it is kind of BDNK theory, MIS theory, well known in the literature, can be applied to many systems. Yeah, I think we can extend this kind of theories. But yeah. What is? Oh, okay. Okay, this very, very important question, I think. My personal impression is that this theory cannot be derived from holography. This theory cannot be derived from kinetic theory, because this is kind of another microscopic theory which is applied to this class of systems, Q sitting near the critical point, magnetohydrodynamics, and these things. So to me, it's not it cannot be derived from holography. Maybe in that way, exactly. Again, Sasho, Nubat, Popotikul, and also Andy Lucas. Yeah, maybe in that way. But holography in the original case, no, I don't think so. Right. 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 Exactly. Yeah. This may work. Right. I see. Good. Yeah. For this theory. Interesting. Yeah. I see. Yeah. Right. Which kind of holographic theory can produce this spectrum? Right. Yeah, that's true. It is okay, very good. The point is, how can we push this to, okay, these two non-hydrodynamic quasi-normal modes, I mean, these two guys. Okay, we have this. Okay, the point is, the spectrum that I started with is not this. I said that I have these two modes, okay, these two modes are kind of close to each other, well separated from the other modes. I think this is a little bit different from the structure of Christmas tree in holography. The thing that I want is this is not similar to, but maybe there are some holographic theories that could lead to this kind of a spectrum. Yeah, ignore. Okay, why? Why should I ignore? Why should I ignore while the distance between these two modes is equal to the distance to these two modes? I don't have any idea to do that. In my case, I see. Okay, good. Okay, question. How to, okay, in what limit these two modes get close to each other? When we increase what, sorry? Okay, right. I see, good. Yeah, I would say these two modes may come to play. In our picture, these modes are fully decoupled. But in holography, as far as I know, in our previous works, we saw that these modes also come to contribute by increasing the value of K, various types. Right. Okay, good. Okay, I don't know any information about the rest of things. I would like to consider this kind of microscopic things. I know that this is not a genuine microscopic theory. I agree with you. Again, I would emphasize that theory B is not universal. I said that. This is universal functions for this class of systems that this theory could apply. Only this. So this is not so universal as diffusion theory. But I should be honest by that. Right. 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 I think I need to discuss in detail with you. Thanks for the comment and question. I need to discuss with you, but I didn't get the point, honestly, in the last part. No, sorry. I was thinking too. Thank you very much.